Understanding power calculations, especially when to apply the square root of 3, can indeed be tricky. Let's break down the voltage considerations for both single-phase and three-phase alternating current, or AC, circuits. For single-phase AC, you directly use the actual voltage, such as 277 volts or 480 volts. There's no need to involve the square root of 3 in the voltage portion of your calculations. However, when dealing with three-phase AC, the voltage you use depends on the type of connection, whether it's a Y or Y connection or a delta connection. For Y connections, you use the phase-to-phase voltage, which is the square root of 3 times the phase-to-neutral voltage. For delta connections, you use the line-to-line voltage. The line-to-line voltage in the balanced delta system will be the same as the phase-to-phase voltage. In the specific scenario involving the fan coil being switched to three-phase 480 volts, it's crucial to determine whether the system is Y or delta connected to know which voltage to use. I will make an assumption it is a Y-configured system. Assuming it's a Y connection, you would typically use the phase-to-phase voltage. In a 480 volt three-phase Y system, the phase-to-phase voltage is 480 volts, while the phase-to-neutral voltage is 480 volts divided by the square root of 3, which is approximately 277 volts. The formula for calculating volt-amperes, or VA, is VA equals voltage times amperage. In this three-phase context, with the 480 volt system and a total current of 21.9 amps, you have a couple of options for how to calculate the total VA, which will yield the same result. Firstly, you can calculate the VA for one of the three phases using the phase-to-neutral voltage 277 volts and the current in that phase 7.3 amps. Then multiply that result by 3 to get the total VA. That is, 277 volts times 7.3 amps equals 2022.1 volt amps, and 2022.1 volt amps times 3 equals 6066.3 volt amps. Secondly, you can use the phase-to-phase voltage 480 volts and the total line current 21.9 amps and multiply this by the square root of 3, since the phase-to-phase voltage is the voltage that occurs between any two of the three lines. The formula would be VA equals the square root of 3 times voltage times current. So, VA equals the square root of 3 times 480 volts times 21.9 amps. Which equals approximately 18,281.4 volt amps. Because it is a 480 volt three-phase system and not a 277 volt single-phase system, you will need to use a 3-pole breaker. To further clarify when to use the square root of 3, consider these points. 1. Single-phase calculations involve only the voltage and current of that single phase, making the VA calculation straightforward. 2. Three-phase power calculations require you to consider the relationship between phase and line voltages and currents. The square root of 3 comes into play when you're using line-to-line voltage and total line current to find the total VA. 3. If you're working with per-phase values, you can calculate the power per phase and then multiply by 3 to get the total power, which avoids direct use of the square root of 3. Now let's talk a little more about Y and delta connections. Y connections are often used for power distribution because they provide a neutral point that can be grounded, offering safety and the ability to supply both phase-to-phase and phase-to-neutral loads. In a Y system, the voltage between any two phases is the phase-to-neutral voltage multiplied by the square root of 3, as already discussed. Delta connections, on the other hand, do not have a natural neutral point unless one is artificially created through a grounding transformer. Delta systems are often used in industrial applications where high starting torques are required for motors. In a delta system, the line-to-line voltage is the same as the phase-to-phase voltage, but the line current is the phase current multiplied by the square root of 3. When it comes to selecting a breaker for the fan coil setup, you've mentioned using a 30 amp 3-pole breaker. This is a good choice, considering that the total current is 21.9 amps. It's important to select a breaker that's appropriately sized to protect the circuit from overcurrent conditions, but not so large that it allows excessive current to flow before tripping. The National Electrical Code, or NEC, provides guidelines for sizing breakers and conductors. According to the NEC, you should size the conductors to handle at least 125% of the continuous load. In this case, 125% of 21.9 amps is approximately 27.38 amps. Therefore, a 30 amp breaker would be suitable. Keep in mind that other factors such as conductor ampacity, ambient temperature, and dirting factors may also influence the breaker size. It's always a good idea to consult the NEC and local electrical codes to ensure compliance. Additionally, consider the inrush current of the fan coils. Fan motors typically draw a high current when starting up and during normal operation. The breaker should be able to handle this inrush current without tripping unnecessarily. Time delay breakers are often used for motor circuits to accommodate inrush currents. The NEC provides guidance on selecting the appropriate type of breaker for motor applications in Article 430. Let's delve a little deeper into the power calculations. There are three types of power to consider: apparent power, real power, and reactive power. Apparent power, measured in volt-amps or VA, is the total power supplied by the source. It's the product of voltage and current, without considering the power factor. Real power, measured in watts, is the actual power consumed by the load. It's the power that performs useful work. Reactive power, measured in volt-ampere reactive, or VAR, is the power that oscillates between the source and the load. It's caused by inductive and capacitive elements in the circuit. The relationship between these three types of power can be represented by the power triangle. The power triangle shows that apparent power is the hypotenuse, real power is the adjacent side, and reactive power is the opposite side. The angle between real power and apparent power is the power factor angle. The power factor is the ratio of real power to apparent power. It's a measure of how effectively the electrical power is being used. A power factor of 1 indicates that all the power supplied by the source is being consumed by the load. A power factor less than 1 indicates that some of the power is being used to create magnetic fields or electric fields, and is not performing useful work. In the case of the fan coil, the power factor is likely to be less than 1 due to the inductive nature of the motor. Improving the power factor can reduce energy losses and improve the efficiency of the electrical system. This can be achieved by adding capacitors to the circuit to offset the inductive reactant. Power factor correction is often used in industrial facilities to reduce energy costs. Also keep in mind that the NEC has specific requirements for power factor correction in Article 480. Let's summarize the key points. 1. For single-phase AC, use the actual voltage directly in your calculations. 2. For three-phase AC, use the phase-to-phase voltage for Y connections and the line-to-line voltage for delta connections. 3. The square root of 3 is used to relate phase and line voltages and currents in three-phase systems. 4. Select a breaker that's appropriately sized to protect the circuit from overcurrent conditions. 5. Consider the inrush current of motors when selecting a breaker. 6. Understand the difference between apparent power, real power, and reactive power. 7. Improve the power factor to reduce energy losses and improve efficiency. 8. Consult the NEC and local electrical codes for guidance on electrical installations. By understanding these concepts and following the guidelines provided by the NEC, you can confidently perform power calculations and ensure the safety and reliability of your electrical system. Power calculations are essential for various aspects of electrical work, including designing circuits, selecting equipment, and troubleshooting problems. With practice and a solid understanding of the fundamentals, you'll be able to master power calculations and apply them effectively in your work. Remember that it is important to verify if the 480-volt system is in fact a Y-configured system, as it may affect the way calculations are done.